Okay. So I hope my lecture slide is visible to all of you.
Sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So welcome back. Okay. So we are meeting after 2 weeks. So we had, I think, all of you had midsem week, I guess. So I presume that all of you performed well in your midsem examinations. Okay. So now I think this is the 14th lecture. Okay. Of this semester so far. Okay. So in my previous lecture, we had discussion about strain aging and dynamic strain aging aspects. Okay, these are like people call it phenomenon. Okay, each one of them call it a phenomenon, strain aging phenomenon, dynamic strain aging phenomenon. Okay. So dynamic strain aging is quite commonly seen in materials containing interstitial solute atoms. Okay. What happens? We do see yield point phenomenon. Okay, that's also another phenomenon. Yield point phenomenon, strain aging, and dynamic strain aging. These are like phenomena which can see in whenever there is a solute interaction with dislocations. Whenever there is an interaction between solutes and dislocations, that time we do see yield point phenomenon, strain aging, and dynamic strain aging. Okay. So when you talk about yield, I think strain aging, it basically indicates that increase in stress and reappearance of yield point phenomenon. Okay, due to when you hold the material after some amount of deformation. Okay, during holding time, that's basically called aging. We do see again dislocations again going to start interact like a previous material. Okay, and there is increase in strength. Okay, the yield stress is going to rise. Okay, during dynamic strainage, during strainaging aspect. So this strainaging typically called static strainaging. Okay, deform the material, hold it. Okay, for a while. Okay, then if you deform it, unload it. Then what we see, reappearance of the yield point phenomenon. Okay, so this is actually quite commonly seen in steels. Okay, so one has to be very careful. Okay, when you deform the material, hold it for a while before forming it. That's going to create problem once again. So one has to soon after some amount of temper rolling. If you go for a temper rolling, we have to form it immediately. If you hold it at room temperature for some amount of time, or it can be some weeks or months, so they would you see again reappearance of yield point. Again, same problem is going to come into picture. So one has to be very cautious. Okay, after temper rolling of low carbon steels, one has to okay form it quickly, without much hold. Okay, that's called strainaging aspect. Then we discussed about dynamic strainaging aspect, okay, which is quite commonly seen when there is a substitutional solid solution. Okay, so when we have a substitutional solute atoms interact with with dislocations, we do see dynamic strainaging during deformation. During deformation, okay, not only substitutions, even some interstitial solutions also can interact during deformation. That can lead to dynamic strainaging. Okay, so basically what you are talking about, okay, the dynamic strainaging is basically reflects in the form of the flow stress can be seen a peak or a plateau. We may see some plateau, or can there be an increase in flow stress with increasing temperature. Okay, so that is basically rises the strength of a material in a certain temperature window and strain rate window. Okay, here we showed only in terms of temperature. It can also be as a function of strain rate also. We do see in a particular window of strain rate and temperature, stress is going to increase rather than decrease. So that can happen. Okay, so this rise in stress with increasing temperature, okay, or maybe maintain constant. So that's basically manifestation of a dynamic strainage. Apart from flow stress peak and plateau, we do see work hardening rate is going to increase. Okay, and coefficient K can also increase. Apart from that, the ductility is going to decrease. Ductility, that's a major problem. Okay, whenever there is a rise in stress, okay, during deformation, okay, with increasing temperature, that can be accompanied with a reduced ductility. reduced ductility. So, and on top of it, we may see some materials will exhibit negative strain rate sensitivity. Materials exhibit negative strain rate sensitivity, and we may see some serrations in flow curves. In stress strain curves, we do see some kind of serrations can be seen in a material. So, all these things basically manifestation of dynamic strain aging. Okay, so I think we discussed okay what basically okay contributes during age during deformation. Okay, depending on strain rate and temperature. Okay, we do see aging. The strength due to aging can dominate the stress drop due to temperature. Okay, so that can lead to increase in stress. Okay, in a particular strain rate window or in particular temperature window, we do see the stress is going to rise due to aging. Okay, rather than okay there will be decrease in stress due to temperature. However, the aging which can happen during the formation in that particular strain rate and temperature window, that can lead to increase in strength or saturation of a stress or strain rate window or temperature window. Okay, I think we had discussion about okay this thing. Okay, then we discussed about different types of serrations. What we see when a material exhibit dynamic strain aging, we said there will be a serrations in a stress strain curve. Okay, if you talk about stress and strain, we do see different types of serrations. A, B, C type. Major things are actually A, B, C, or combination of A plus B can be seen. A plus C can also be seen depending on okay conditions. So major things what we see, it can be A type, B type, or C type serrations. Okay, here I said okay depending on strain rate and temperature window, we may see there is a window. Okay, the material can exhibit serrated flow behavior. Okay, okay apart from okay if we go away from this window, we do not see serrations in the same material. It basically indicates that dynamic strain aging can occur okay over a range of strain rate and temperature, but there is a window beyond and below and above we don't see serrations in the material. Okay, so this basically serrations basically indicates that there is a localization of strain in the form of a deformation bands. Okay, this is basically due to inhomogeneous plastic flow. Okay, these serrations like yielding serrations what we see. Okay, so these serrations basically indicates that deformation bands are going to okay form. Okay, that basically related to strain localization. It can happen. It basically indicates that there is a inhomogeneous plastic flow during deformation of a material. Certain materials, not every material. Only certain materials will exhibit dynamic strain aging. Okay. So I think here, I think at this point, I think I stopped my previous lecture. If there are any doubts, please let me know. If there are any doubts, please let me know. No doubts? Okay. Am I audible to all of you?
Yes, sir.
Okay.
Yes, sir.
I'm wondering. Okay. Yes. Okay. So I think with that, I think after that, I think I also floated assignment deadline. Okay. Yesterday was the deadline. Okay. I hope all of you submitted the assignment. Okay. Okay. So now I think we'll discuss. Okay. Just one more, just little bit of information. I think I expected some of you will ask. Okay. Under what conditions the A, B, C will form. Okay. Because I said there are different types of serrations, but I didn't discuss. Okay. Under what conditions A, B, C type of serrations will form. What is the difference? Okay. Between A, B, C. Okay. So what is the difference between A and B? What we could see the difference between A and B? Just I think I'm just okay putting it in a different. Okay. What is the difference between A, B, C here? Can anybody say? What is the difference here we are seeing between A and B? At least first say.
Frequency is increasing.
What is that?
Frequency is increasing.
Frequency is increasing. Okay, fine. But between B and C,
Increase in amplitude.
Sir, this hump, I mean up and down, generally is representing dislocation interaction, right?
yes.
So if the curve A and curve B, so curve B is showing clearly the high amount of dislocation interaction,
Okay. Okay, good. Yeah.
and curve A has less extent.
Okay, good. Yes. Okay. Yeah. So I think you're right. Between B and C, what is it? Okay. If you see, okay, your stress strain curve, okay, supposed to follow like this. Am I right? Okay. If there is a strain work hardening, it's supposed to form, okay, it's go form like this if there is no serrations. But what happened when there is a serrations? What happened? The serrations happening below this, okay, regular curve. Okay. Whereas in case of B, we are seeing serrations within that. Okay, there is a work hardening, but at the same time, serrations happening in the same general, okay, stress strain curve, following a general stress strain curve. Here in type C, serrations are happening below the general stress strain curve. Okay, so between A and B, okay, the frequency, okay, is changing of the, okay, the frequency of the stress drop is changing. Here in A, we are seeing initially work hardening, some amount of work hardening, sudden rise in stress followed by sudden drop. Okay, again going to strain hardening portion. Again there is a drop, extra rise in stress, again drop. Okay, so this is actually, or okay, some amount of, okay, gap is there. So in the type A is, okay, if you look at here, I just listed down, okay, what conditions can, okay, give us type A, type C. Okay, type A.
ठीक है प्रॉब्लम नहीं है मैं कवर कर ये लंच टाइम में बंद होता है फोन
Hello,
ऐसा
Sweta, can you switch off the, can you switch off the mic? Okay. So the type A, type B, type C. Okay, what you are talking about? Type A. Okay, we are seeing a rapid rise in stress initially, then sudden drop. Okay, again following regular work hardening path. Again there will be a rise in stress, little bit drop in stress. Okay, so this, okay, happening over a period. Okay, some gap is there. Okay, so this type A serrations called locking serrations. They are called locking serrations. Okay. And type C called unlocking serrations. These are happening below the general stress strain curve. These are called unlocking serrations. Okay. So the temperature and strain rate, okay, is going to, okay, the window is going to change for type A, type B, and type C. Okay. So here I listed down type A serrations. Basically, these are periodic, okay, serrations from repeated deformation bands initiating at the same end of the specimen and propagating the same direction along the gauge length. It usually happens, okay, when, okay, temperature is low and strain rate is high, okay, as compared to other type B and type C serrations. And the type B serrations, okay, typically, okay, can occur, okay, when there is a relatively high temperature and low strain rates as compared to type A. Okay, type B can be independent, can also come after type A. After certain amount of type A, we may also see type B serrations can continue. Okay, can basically successfully after type A, we may see type B also. A plus B type also can be seen. Okay, serrations depending on the temperature, strain rate, and the amount of solute atoms precipitates. Okay, so some scientists also participate. So depending on amount of solute atoms and the type of the difference between the atomic size between solvent and solute can also give, okay, this kind of interactions. And that in case of type C serrations, what we are talking about, okay, these are going to happen below the regular, okay, stress strain curve, and this usually happens, okay, higher temperatures and lower strain rates than the case of A and B. Okay. So it is very important depending on type of, okay, alloying element, how it is, okay, each size is different from solvent material, matrix material. Okay, that basically gives us interactions between the solute and solvent. Okay, between the, okay, solute and the dislocations. That interaction can be of, okay, type A, type B, type C, or we can also see type A plus B, type A plus C. Okay, can also be C. Okay. So depending on, okay, strain rate and temperature combination. Okay. Is it clear? Okay, this is whatever we discussed so far. Okay, in previous lecture and today, these are like a, okay, what we are talking about, instability things, plastic deformation, instability conditions, like what we are talking, the phenomena, what you talked about, yield point phenomenon, strain aging, dynamic strain aging. These, okay, will be plastic instability things. So one should avoid these things. If there is this kind of bands, then that means we are going to see formation of a rough surface. Okay, the rough surface creates a problem in the finished components during, okay, after forming. So one has to avoid this, okay, plastic instability conditions what you can see in some certain materials. Okay, is it clear? That means you have to deform material, that strain rate and temperature has to be changed so that we do not see this kind of, okay, solute and dislocation interaction. So this is quite commonly seen in aluminum alloys, aluminum magnesium, aluminum lithium alloys, aluminum copper lithium alloys. Okay, where would you see the, okay, the solute atom size is going to be much smaller than, okay, solvent material. Okay. So typically greater than 12% difference. Okay, if there is a difference of radii is about greater than 12%, we do see, okay, this kind of dynamic strain aging. Simply call it, in non-ferrous materials, we call it as a Portwin-Lee-Chatelier effect. Portwin-Lee-Chatelier effect. Portwin-Lee-Chatelier effect is a subset of dynamic strain aging. Okay.
Sir,
So
any
this,
reason why they're called locking or locking and unlocking?
no,
Type A and Type C.
it basically continuous unlocking happens. Okay, in this temperature, if you go to higher temperatures, okay, where you are giving it enough, okay, diffusion to take place, okay, your amount of deformation is less, completely unlocking happens. Okay, slowly starting, okay, getting unlocking during deformation. Here actually this lock is going to lock again, unlock again, lock, unlock. Okay, it basically simply is all locking can happen. Okay, some, that's why you see increase in stress than the, okay, your regular stress strain behavior. In this case, your stress is not increasing. Okay, stress is dropping basically below this level. Okay, here actually we do see a lot of, okay, unlocking happening between the solutes and dislocations.
Understood.
Yeah. Okay. Any more doubts here? Because that's the end to the, that what we discussed, yield point phenomenon, strain aging and dynamic strain aging phenomenon. So if there are no more doubts, I think start new, okay, topic. Okay, crystallographic texture of materials. Okay, so crystallographic texture, it's one of the, okay, subset of microstructure. Subset of microstructure. Okay, microstructural aspect. There are several microstructural aspects. Grain size one of them. Okay, apart from grain size, another important is a crystallographic texture. So in some universities, some institutes, okay, they do take this. Faculty will offer a dedicated course on crystallographic texture of material. So it can run. People do run the course for, okay, almost 4 months, complete full semester. So, but actually in this I cannot afford. Okay, so I can only, I'm giving only as a one topic. Okay, I may just give only up maximum 2 lectures, 1.5 to 2 lectures. Okay, so I'm trying to concise some important aspects, okay, which are, okay, which we have to know, okay, in order to understand, okay, the terminology related to crystallographic texture of a materials. So most of the information I've taken from some review article and some from this textbook. Okay, so I think I learned this topic from, okay, my, he is my one of my, okay, I think teachers, okay, Professor Satyam Subhas from IISc Bangalore. So during my PhD time, I learned about some aspects related to crystallographic texture. He is expert on crystallographic texture, and here we have a Professor Samazdar who is also expert on crystallographic texture of materials. Okay, so a lot of texture related studies will be conducted. Okay, in India, I think there are a lot of people are working. Okay, so Professor Satyam Subhas and Professor Samazdar, those are experts. Okay, and Nilesh Gurov is a student of Professor Satyam Subhas. He also, okay, he has expertise on the crystallographic texture. I have limited expertise, but whatever I learned, whatever I understood, okay, after reading some other things, so I'm going to deliver those things in this, okay, today's lecture and followed by next lecture. Okay, is it clear? Okay, so before starting this content, okay, crystallographic texture, so I hope all of you remember, I think, okay, remember that there is a quiz exam this Saturday. Okay, it will be conducted. Okay, So as per the schedule, I think 4 to 5:20, that was the thing decided in my first lecture. So up to today's lecture, okay, will be covered. Okay, from the after quiz one, whatever okay portion okay, started. So that whatever not covered in the quiz one will be covered. Okay, up to today's lecture. Okay, so prepare well. I think prepare well and do well in the exam. So be ready with for the
Sir,
quiz 2.
even crystallographic texture,
Yes,
whatever we teach today, will be there, right?
yes,
Okay.
you're right. Yeah, till today's lecture. Okay, Friday's lecture will not be part of it. Okay, like last time also I did like that. Okay, Friday's lecture was not part of the quiz one. So that okay, that day onwards, okay, that Friday lecture onwards to till today's lecture will be covered in quiz 2. Okay, so quiz 2 will be also for 20 marks. So you know quiz 1, quiz 2, quiz 3, best 2 out of 3 will be taken for the consideration. Okay, for grading consideration, 2 out of 3 will be considered. It's up to you. Okay, if you want to appear, okay, depending on okay, you can decide whoever wants to appear, they can appear for the this thing. So is it clear? I think now I think I'll start okay a new content related to okay new topic related to crystallographic texture. Okay, so the crystallographic texture okay is basically the texture word texture has come from okay word textor okay like a it basically means weaver in the Latin okay weaver. So the texture okay is quite common. We see okay in sarees which is some kind of texture. Okay, with cloth will have some texture. Okay, even composites will have some kind of texture arrangement. So this texture is a common okay word. Here what you are talking about in polycrystalline materials okay grains will arranged in a particular fashion with certain boundaries okay separated with the boundaries. Okay, if you look at here, if you take a sheet okay a sheet okay, so if you talk about assume that it's a cubic material okay, it can be BCC, FCCR okay, some simple cubic kind of thing if you assume. So if you consider a cubic material okay, each grain okay on a surface we see it will have a particular orientation okay orientation here. If each grain is randomly oriented okay randomly oriented it's called okay a textureless material. It's also called randomly oriented material. Randomly oriented material. When in case of textured material means there will be some preferred orientations. Preferred orientation. That means some of the grains, okay, major part of the grains will be oriented in a particular okay orientation with respect to your sample direction. Okay. So what we are having? We have a crystal structure. Okay, we will be having crystal structure. It has its own system. Okay, crystallographic system. It has directions and planes. Okay, and we also have a sheet. Assume the sheet will have a its own okay sheet directions. Okay, rolling direction, normal direction, and transverse direction. Okay, so we are having coordinates okay specific concepts called sheet or specimen coordinates, and we also have a coordinates with respect to crystal structure. Okay, here when you say fully textured sheet, what does it mean? Okay, majority of grains will be oriented in particular direction with respect to particular direction of a specimen or sheet. Here for example okay assume that okay 001 grains okay which are actually crystal coordinates 001 grains planes okay are oriented parallel to most of the grains were oriented with respect to normal direction okay sheet normal direction. Okay, so this is called cube texture. Okay, this is called cube texture. Okay, one can also represent in the form of a plane. Here actually direction 100 direction parallel to RT. Okay, it's called cube texture. If it is this is one example of telling. So if you look at the face of a grains which are of a 100 or 001 grains are okay are parallel to NT direction. Okay, so this is called cube texture. Okay, this is one example I'm showing. Okay, so and some another example. Okay, here okay here one I think one of my peer students okay Javed he did actually okay, he's working on copper. Okay, copper has initially has this kind of texture and it was deformed under biaxial condition under biaxial deformation. What happened here? Majority of grains now transformed to okay look at here the grain color has been changed. Am I right? Okay, so the same material when it was deformed under biaxial condition okay, we do see some deformation texture has been developed here. We could see strong, okay, 101 texture it become more dominant, okay, as compared to your initial undeformed condition. So this is basically the initial we have almost like a okay, textureless or a randomly oriented, close to random orientation. But after deformation, we do see majority of grains have transformed to okay 101 texture. Okay, some kind of
Sir.
yes.
Sir, I was thinking like if the orientation is preferred or in a certain direction, let's say 001. So it means there are no twist between grains. I mean, they are at the certain orientation. Crystallographic planes are in the same direction. So some part will looks like same only. So how will we differentiate the two different grain?
No, no. See, if it is the same, but there will be small variation. Okay, there will be some boundary is
Okay.
going to exist. Okay, some
Mm-hmm.
boundary is going to exist during deformation. Look at here. It's very hard to identify a boundary here. Okay,
Okay. Yes, sir.
okay. So, but they will exist. Okay, there will be some low angle boundaries will exist.
Mm-hmm.
Because of twist. Okay, we may see some kind of okay rearranged boundary also going to get rearranged. We do see during if it is a deformation, we do see a lot of okay low angle boundaries are going to generate.
Mm-hmm. Okay, sir.
Yeah, you are right because if it is the same orientation, why should there be a okay boundary? But
Yes,
okay,
sir. Yes.
but this might have already we have polycrystalline material during deformation or during some other process. We may see some grains are going to get rotated or twisted. We can say rotated, so that can give
Mm-hmm.
us the same kind of orientation. Still, there will be a slight okay
Slight
misorientation
misorientation. Yes, sir.
going to exist. Okay.
Yes, yes. Okay, thank you,
In
sir.
this case, we are going to see more low angle boundaries. Okay, as compared to high angle boundaries.
Okay, okay.
Yeah, it's good doubt. Yeah, it's not. Okay. So here, okay, so this is what called actually texture, crystallographic texture of polycrystalline material. What we discussed about polycrystalline materials. Okay, polycrystalline material constituted from a large number of small crystallites. Okay, each of these crystals has a specific orientation of the crystal lattice. If the specific orientation is mostly in a particular orientation dominating, then we call it the material is a textured material, okay, or preferred oriented material. So what is actually okay? We do see, for example, in cubic materials, certain orientations can be developed. Okay, there's a possibility of okay. If we take a sheet, we may see this particular orientations can develop. If you look at here, this is a 10001 plane. Okay, is a parallel to 110. You decide. Okay, so we may see certain orientations can develop like this, which with respect to what you are talking about, crystal coordinates. These are coordinates with respect to rolling direction. Similarly, hexagonal materials, okay, not only cubic materials, hexagonal HCP materials also can undergo okay, development of a texture. Okay, some examples here I shown. Okay. So, what is the effect of crystal? Why do you need to study crystallographic texture? Okay, it's like a microstructure, right? It's subset of a microstructure. So, crystallographic texture also has significant influence on certain properties. Okay, the properties are going to get affected okay, depending on crystallographic texture of the material. Can anybody say some examples which properties are going to get affected? Which properties okay are going to get affected?
Sir, impact strength because there will be less stress razors on the surface.
Yeah, there's some fracture toughness also going to get affected, okay, relatively. But yeah, but some important which will be known very easily. Okay, we know. Okay,
Sir,
we usually
tau C.
what is tau C?
Sir, tau C. Critical resolved stress.
Yeah, your stress basically depending which orientation is okay favorable to the loading direction. Okay,
Yes.
okay that basically your yield strength is going to get affected. Okay, am I right? Because once if tau C is getting changing means your yield strength of the material is going to change.
Yes, sir, yes.
Yeah. So anything else? Some basic okay because see we are talking about the material properties can be isotropic or some can be anisotropic. Am I right? Am I right? What is meaning of isotropic property and anisotropic property?
Yes, means isotropic means you don't have any preferred orientation. Means rolling. If you are doing rolling, so all the grains are oriented in the single direction. So we can tell there is anisotropic nature. So
Okay,
it means
isotropic
directional
property.
property. Yes.
Yes,
Yes,
okay,
sir.
isotropic. Okay, the properties which do not depend on direction, those are called okay isotropic. Okay, nature. If they depend on okay, direction, these are called anisotropic materials. Okay, most of the materials will be anisotropic in nature. It means, okay, the property is going to change depending on direction. The simplest one, elastic modulus. If you take elastic modulus, okay, it's a highly dependent on direction. Okay, which if you take a simple cube, okay, the direction, depending on direction, okay, your elastic modulus is going to change. Okay, so elastic modulus is strongly anisotropic properties, depends on the okay, direction of the, okay, depending on which direction you're talking about. It comes from a bonding. The moment bond, okay, direction changes, bonding is going to change. Okay, so that can influence the, okay, elastic modulus of property and yield strength. Okay, many properties. Okay, I'm talking even fracture strength also people showed. Okay, fracture strength is going to depend on, okay, fracture toughness. Okay, many properties are going to get affected which are, okay, anisotropic in nature. It can be affected by changing the texture of a crystalline texture of a polycrystalline material. Okay, the most important thing, okay, formability. Okay, so I listed down some of the things. Okay, and okay, formability as far as deformation is concerned, okay, formability is going to get affected. Okay, and as far as, okay, magnetic properties, okay, we know, okay, silicon steels, iron silicon steels are used for what purpose? Any idea? Silicon
Sir,
iron
Transformer.
transformer,
transformer
hysteresis.
cores.
Yes.
Okay, transformer cores, those are called, okay, gas oriented, non-gas oriented, okay, iron silicon steels. So those, okay, the property, the magnetic property is going to depend on what texture. It has specific texture. Okay, gauze is called gauze texture. Okay, we would need to have a gauze texture so that we can have a minimum loss in the thing. So that actually your electric, whatever loss you're talking about, okay, eddy current, all the loss will be minimum if the sheet has a particular orientation. That's orientation. Preferred orientation is a gauze orientation. Okay, so there the property, okay, those sheets will always have a particular texture in order to have a minimum loss in the, okay, current or magnetic power in the course. So here one example I'm talking about is this actually electrical magnetic properties. I don't spend much time. Formability. If you talk about formability, can anybody give some example where the texture is going to influence formability? One example for formability. No idea.
It means if
Some component. Some
sample is,
component. Yeah, some
yes,
component.
if the sample is textured or rolled, we need to anneal or make it softer to make any forms or to give you any mold or shape. So formability is definitely going to affect it if you roll it.
Okay. Yeah, formability is going to get not only rolling, heat treatment also can give you the changes in the formability. Okay. One best example, beverage cans. Okay, we talk about the beverage cans. Okay, all of you I think might be using, okay, might use, okay, these things. Okay, Coca-Cola, okay, or Pepsi kind of cans. Okay, those are made of aluminum beverage cans. It usually formed by deep drawing, by taking a blank, okay, blank sheet and deep draw it at a different levels. Okay, finally we get a this kind of, okay, can out of it. Okay, so when you deep draw on it, okay, we do see, okay, this kind of, okay, defect. Okay, sometimes the preferred one is actually should be like this. Okay, but we do see some this kind of defect. These are called ear defects. Okay, these are called ears. Okay, so these ears, okay, have to be minimized. Otherwise, what happens? There is a huge loss to the company. Okay, because this we have to cut it out. Okay, you have to, okay, discard this top portion if I want to further, okay, deep draw it. So that actually one should avoid. Okay, if you can avoid this earring defect, that means actually it's very good. Okay, the material actually can be drawn to a certain shape, certain size. If there is a earring defect, that means there's a loss, huge amount of loss to the material, wastage will be there. Okay, so much, okay, cost is involved. So this aluminum, okay, whatever talking about aluminum alloy, okay, some commercial, some aluminum alloy is used for these kind of things. With this initial blank, the sheet will have a certain crystallographic texture that can minimize, okay, that can minimize this earring defect. Okay, I'm talking about aluminum cans. Okay, even some of the, okay, if we talk about body, automatic body parts, we use interstitial free steel. Okay, so when you form it, that component, okay, you should avoid, okay, some defects. Okay, like this kind of defects have to be avoided. So that can be avoided if you have a particular, okay, R bar value. It's called R bar. Okay, so formability is assessed in the form of a Langford parameter, R bar value. So, okay, higher the R bar value, lesser the defects. Lesser the defects what we can see during drawing or forming operations. Okay, so the texture there, the texture plays significant role, okay, to minimize wastage in the material, okay, and also basically minimize the defects formation during forming of a component. Okay, so texture, this is a significance. Okay, the properties are going to get affected, okay, especially the formability and magnetic property. If you see some examples, we talked about iron silicon alloys, and formability is aluminum and IF steel, industrial steels will undergo some drawing operations. Okay, earring is one of the common defects if you do not have a higher R bar value. Higher R bar value, okay, anisotropy parameter, anisotropy parameter, okay, it's also a Langford, okay, parameter. It's basically, okay, when we have a good texture, some preferred texture, that is going to minimize the this kind of defects. Okay, so this is the kind of, okay, effect of crystallographic texture. Okay, then how this texture, okay, what kind of process can induce texture formation? Okay, we expect that material, polycrystalline material, has to be random in nature, but because of certain processes, okay, we do see the texture is going to get formed. Okay, there will be some preferred texture is going to develop. Okay, it's going to be developed in the material. Okay, under what kind of process we do see texture development is going to take place? Can anybody say? Okay, initially, for example, okay, we expected to have a random texture, but because of some process, we do see that the material is going to have some preferred texture. What
So
kind of process?
mostly all forming process like forging, rolling,
Yeah, so
we can see the texture.
whatever plastic deformation is involved, okay, plastic
Yeah,
deformation
right.
can induce some texture. Okay, that texture is called deformation texture. Okay, one actually because of slip activity, twinning activity. Okay, at some, okay, we do see some texture is going to get built up. Okay, that's one example I already showed. Okay, copper thing. Okay, we have taken a undeformed metal. If we deform it, we do see texture is going to develop. That's called deformation texture. Any other process can also induce texture formation.
Sir,
Solidification.
Solidification, yeah,
etching,
right. Okay,
etching could
solidification.
also
Sir,
form.
sir,
Yes,
spinning,
which one?
fiber spinning, sir.
Yeah, fiber metal. If we are talking about, okay, metallic materials, usually, okay,
Okay.
polycrystalline materials. Okay, in polymers we don't see, okay, we do not talk crystalline texture there. Okay, we talk about their morphology there. That's different. Okay?
Sir, recrystallization.
Yeah, so recrystallization, heat treatment can give you, okay, annealing recrystallization can give you. So one I talked about, okay, solidification, basically okay, crystallization process, any crystallization process. Okay, if there is some crystallization of liquid to solid transformation, okay, so solidification can give you, okay, and even phase transformation, for example, even in solid state, okay, when austenite transforms to ferrite, okay, then also we do see change in a texture. Okay, so what we are talking about, the process which can induce texture in a material, crystallization process, like a solidification process. The second one, recrystallization process. Phase transformation within solid state can also induce, okay, texture change. And most important is a plastic deformation. Okay, even some process like a thin film deposition or electrode deposition, those can also induce texture, okay, in the material. Okay, it's basically summarized here. Okay, crystallization, solidification from a non-crystalline liquid state, we do see texture can build up, and recrystallization from the same phase, Okay, what you are talking about? Grain. Okay, if there is a recrystallization happen, deformed material, it need undergoes recrystallization. Okay, that can also change the texture of the material. And phase transformation can, okay, from austenite to ferrite transformation can give a change in, okay, texture. And plastic deformation, blood white, slip and twinning activities can induce texture change in the material. Apart from these four, we also talk about, okay, thin film deposition, electrode deposition, some kind of process can also induce texture in the material. Okay, so the texture change, what texture change is going to also going to depend on crystal structure of the material. Okay, these are basic formation process. Okay, the texture change what you're going to see, it basically depends on crystal structure and also sample symmetry. That means what type of deformation you're giving. Are you giving uniaxial deformation? Okay, wire and rod, it will have particular same material, but the texture may be different. Okay, biaxial conditions will get different texture. Triaxial state of, okay, if you give triaxial state of stress, we do see the type of texture that can develop is going to be different. If you give only shear deformation, the texture deformation is going to be different. Okay, so apart from this formation process and the type of texture that's going to develop is going to depend on crystal structure and the sample symmetry with respect to, okay, kind of, if we talk about only deformation, within deformation, okay, what type of deformation you're giving, that can also change the texture of a material. Okay, so what factors decide the crystallograph texture? Okay, there are several, because already we discussed this process. Each process has its own parameters. Okay, it has own some parameters. Okay, once you change a parameter, okay, once you change the parameter of it, okay, talk about deformation. If you change the strain rate, if you change the temperature, if you change the amount of strain, okay, that can change the texture evolution. Okay, even if we talk about stacking polyages, okay, low stacking moments, high stacking moments will not give same type of texture. The texture is going to be different. Okay, I'm just giving example. Okay, even we get a deformation texture, even if you take FCC material. Okay, depending on stacking fault energy, the texture development for the same amount of strain, same strain rate, same temperature, the texture development is going to be different. Okay, even if you change the strain rate, okay, at low strain rate, high strain rate, we may not get same texture evolution. Okay. So like that, okay, there are several factors. Okay, there are n number of factors which can decide that, okay, which can dictate the type of texture which is going to be built, okay, in the polycrystalline material. Here I summarized, okay, some of the important depending crystal structure, deformation system, material, solid state impurities, insoluble impurities. There's so many things. Okay, initial texture, initial grain size, okay, that can dictate what type of texture is going to build up. Strain rate, okay, amount of deformation, mode of deformation, temperature, annealing temperature, okay, heating, cooling rates, furnace, all these things, okay, can influence what type of texture is going to form in a given material. Okay, this is some, okay, example. I give some parameters, some factors which can, okay, there are many factors, but as far as deformation is concerned and heat treatment is concerned, okay, these parameters are taken into consideration here. Okay, so now I think we talked about, okay, how the textures are going to form and what factors are going to dictate. Okay, how to characterize, okay, crystallograph texture of a material? Any idea how do you characterize? Okay, now you have to, okay, characterize the texture in a material. What kind of tools will be used to characterize crystallograph texture of a material?
EBSD,
Okay, what is EBSD?
backscattered,
What is that? What
electron
is
backscattered.
electron
EBSD,
backscatter?
sir.
Yeah,
What is
yeah.
electron
EBSD.
backscatter?
Yes, sir.
Electron backscatter?
Diffraction.
Dissection,
Diffraction.
yeah.
Diffraction. Okay, that's called EBSD. Okay. Anything else we can use?
So X-ray.
X-ray, yes, yeah, X-ray, X-ray diffraction. Anything else?
Can we go with the neutron also?
Yes, neutron diffraction. Yes, you're right. Yes. Okay. Yeah. So most of you are right. Okay. X-ray diffraction for most important one. Okay. Then electron diffraction. Okay. With electron diffraction, basically we can use, okay, SCM, and with SCM EBSD we can use, with the TEM also we can get, okay, with the transmission electron microscope also we can get texture information. Then, okay, neutron diffraction, synchrotron diffraction. Okay, people also use some ultrasonic, okay, things also. Okay. So these are kind of, okay, methods are available, okay, to characterize, okay, crystallograph texture in a given polycrystalline material. Okay. Most commonly used is X-ray diffraction. Neutron diffraction is used only when there is, okay, problem with the X-ray diffraction for given some better materials. Okay, the peaks can very close by. So in that case, we do use neutron diffraction. Electron diffractions can also be used, EBSD and TEM. Okay, synchronous diffraction is powerful, very powerful thing. Okay, but it's very high. Okay, costly. thing. We don't have everywhere, okay, the synchrotron facility, but the penetration will be more. We can get more information from the synchrotron diffraction. And ultrasonic methods are used like a just qualitative purpose. There's not much, okay, literature exists, but very few occasions people could figure out the difference in the wave, because the wave, okay, is going to different depending on the texture of the material. Okay. So based on the wave change, people could use to get established, okay, the texture in the material. Okay. So the crystalline texture is classified into three types. Okay, macro texture, micro texture, and meso texture. Okay. Macro texture, what you are talking about, bulk. Okay, it covers so many grains. Okay, it goes to 3D kind of thing. Okay, three-dimensional information. Micro texture is like a only surface, okay, information. Surface information will be gained. Okay, macro texture is also called bulk texture. Some people call bulk texture or macro texture. Micro texture is basically, okay, surface information. Okay, localized information will be collected. Okay. For macro information, one can use X-ray diffraction. For micro information, okay, we use, okay, EBSD, SCM, TEM will be used to get a surface information, okay, in the material. So synchrotron is used, okay, for the bulk texture, macro texture information. Neutron diffraction also bulk texture information can be obtained. Okay. So meso texture is actually related to, okay, boundary misorientation also will be taken into consideration. Okay. Meso texture basically considers boundary, okay, axis and boundary misorientation. If you consider in the texture, that's called meso texture. Otherwise, basically we have a micro and macro texture. Okay, macro basically covers so many grains, okay, go deeper, okay, much deeper. Okay, volume wise, we get a volume information. SCM only get a surface information. Okay, as if you use SCM, EBSD, TEM, we get a kind of surface information of the texture. Okay, so these are the techniques available to characterize crystalline texture of a material. If you talk about X-ray diffraction, okay, I guess all of you know how the X-ray works. Okay, X-ray diffraction. What law is used? What is the law, governing law, which is used for X-ray diffraction?
Bragg's law.
Bragg's law. Okay. So it basically X-ray diffraction works on, okay, concept of, okay, Bragg's law. Okay, and okay, 2D scientist is equal to m lambda. Okay, the Bragg's law. Okay. Once you have atomic arrangement, we do see once you send the X-rays, those some of them are going to get diffracted depending on structure factor of the material. We do see, okay, certain, okay, constructive interference is going to happen. So we can get actually what type of, okay, information. Okay. So typically the instrument, okay, if we talk about regular, okay, X-ray diffraction. So X-ray diffraction. So theta to theta scan typically people perform. We send X-rays onto the sample, and diffracted rays will be collected by a detector. So this detector is going to move at, okay, certain rate. Okay, it's going to move at certain rate. In some X-ray diffractions, people what they do, some people they do X-ray tube also, okay, may also both will do, but sample will be fixed. Sample is at a fixed condition. Okay, there's no change. Okay, it's a static. Okay, some, okay, X-ray, some X-ray source will be fixed some cases, and only detector will be moved. Only detector will be moved and collect the, okay, diffracted, okay, rays, and establish, okay, number of counts per particular, okay, orientation, how many orient coming. Okay, so typically we establish a, okay, from this X-ray diffraction we get a plot counts, okay, in y-axis, and Bragg's law. Okay, 2 theta, typically we take a 2 theta on 2 times of a Bragg's law, Bragg's theta we use actually. So 2 theta will be used. So typically, okay, your x-axis will have a 2 theta and counts on y-axis. So we do get, okay, a kind of, okay, some peaks will be there at certain Bragg, okay, angles. At certain Bragg angles, okay, each Bragg angle corresponds to particular, okay, plane. Okay, particular plane. For example, here if we talk about, okay, one is a, I'm talking about, I've taken a, okay, information from one of my students' work. Okay, he worked on some nickel sulfur based foils, and he varied the sulfur content. Okay, just varied the sulfur content, and okay, he produced by electrodeposition. Okay, here, okay, for example, NS means negligible sulfur, 30 ppm, and VHS means very high amount of sulfur, 1200 ppm sulfur. Just here, by changing the sulfur, okay, he got the foils, he got different foils and did X-ray diffraction, regular theta, 2 theta. Okay, Then with changing the sulfur content, what he had seen some changes in the, okay, the peak intensity has been changed. Initially, we are getting a particular peak. This particular peak is corresponds to 200. Okay, nickel is FCC. We get for FCC, we get, okay, 111 peaks, 200, okay, 220, 3111, okay, 34, okay, 8, okay, we get actually, okay, 8, 11 kind of, okay. So you know that, okay, 1 square plus 1 square plus 1 square, okay, basically gives, okay, 3, 2 square plus 0 plus 0, 4, okay, 3, 4, okay, h square plus k square plus l square, okay, we talk about, okay. So 3, 4, 8, 11 kind of combination we'll get. So look at here. So 200 peak is initially stronger. Okay. The moment when you add more and more sulfur, what happened? That 200 peak intensity has come down and 111 peak intensity is increased. What it indicates, can anybody say? What does it mean here? With some alloying, okay, with some alloying, okay. Is there a change in, yeah. Now what does it mean actually?
So, sir, intensity or the height of the peak depends on the atomic position. So, the structure factor that we get, so sulfur is disturbing the atomic position. So, structure factor will reduce. So, intensity will also reduce.
Intensity, okay, no, Bragg angle, okay, related to, okay, plane, okay, correspond, okay, a particular plane, okay. We have a crystal, we have a polycrystalline material, so many grains are there, okay. So initially 200, okay, more grains, okay, of 200 grains are of more in number, okay. The moment when you add sulfur, what happened? This with increasing sulfur content, okay, the kind of growth, okay, your 200 texture more initially we have, that is tending towards 111. Now more 111 grains are forming rather than 200 grains. Okay, that it basically indicates, qualitatively it indicates that, okay, the material initially have a 200 texture. Initially it has a 200 texture. However, with increasing sulfur content, the texture, the ratio, if you take a intensity, okay, area under this curve, okay, in each peak, if I make a, okay, ratio between I200, intensity of I200 by I111, okay, what happens? Okay, it basically decreasing, okay, the ratio is going to happen to be decreasing with increasing sulfur. That means the texture change is taking place. That means more number of grains are forming, okay, one grains are forming, okay, with increasing sulfur in the material, okay.
Uh, so, these are the planes. I mean, these are not the orientation, right?
Yeah, we can take into, because in FCC, okay, with cubic materials, you can also convert into
Okay, okay, yes, sir, yes, sir. I mean, the normal to the direction of plane is same only.
Yes,
Okay,
yes,
yes,
yes.
sir.
That's why we call, okay, with respect to growth direction, these are obtained by electrode position. With respect to growth direction, we have a, when it's a growth direction, we talk actually direction, 200 direction, okay, with respect to growth direction, 111 direction with respect to growth direction. So we are seeing a, okay, the change in a texture. Okay, so this clearly says that, okay, the number of, okay, particular, okay, number of, okay, particular orientation grains is changing by changing the alloy content. Okay, so it basically, this 2 theta scan is going to give you, depending on intensity change, the ratio of change, okay, can tell you some texture change, but it is only just a very, okay, qualitative information. We cannot quantify directly, okay. Indirectly we are saying the intensity changing, okay, but it's not really giving us any quantification. Okay. So that's where actually your regular theta, 2 theta normal X-ray diffraction, okay, will not be used for quantifying crystallographic texture of a material. But it can give you some qualitative information. Some texture changes taking place. Okay. So this is a first cut always people do. First do normal, okay, theta, 2 theta scan and see any change there or not. Okay. Then in order to quantify the texture of a material in a better manner, okay, people use, again, use still X-ray diffraction, but of a different type of XRD machine. The instrument is going to have a different type of setup. Okay, here we'll have a simple goniometer. It's called goniometer, basically rotation. Okay, we'll be having some complex goniometer. Okay, So in order to quantify more, okay, in a precise manner, okay, people use, okay, diffraction in polycrystal by using a Schultz reflection geometry. Okay, the geometry is going to be different slightly. Okay, there the specimen was fixed initial. Here what happens, the specimen will be rotated, oscillated. Okay, so here actually source and detector will be fixed. Okay, what we do, specimen will be rotated, so that, okay, that particular, okay, orientation, how many grains are there, okay, we give oscillation, whatever grains having a particular orientation, those will be collected here. Okay, so particular pole, which we talk is a particular pole. Now it's in this one, each one of them called is a pole. Okay, it's 200 pole, 111 pole kind of thing. Okay, we collect, okay, more information at this Bragg angle, and how many, okay, grains are there in the material will be covered, okay, by just rotating sample with the same fixed, okay, theta, okay, angle. And we also collect information another pole. Okay, we also collect other information. Okay, 3 to 4 poles will be covered. Okay, by using the Schultz reflection, we rotate the sample, okay, such a way that we get a particular, okay, angle, theta angle, and, okay, that particular angle covers particular pole. Okay, once it's rotated, we'll get another, okay, difference, okay, another theta angle. So at the same time, the sample will be oscillated so that more number of grains can participate in the, okay, diffraction conditions. So this thing, okay, this particular, okay, principle is used to quantify, okay, crystallographic texture of a material. Okay, it requires a specialized mechanized, auto mechanized, okay, stage goniometer, where actually the sample will be rotated, okay, so that you can get a particular theta Bragg angle, and it also will be oscillated so that we can cover more number of grains. Okay, so then we collect more information, that once we collect the information, we can quantify it, what type of texture is forming in a material. Okay, so this is another, okay, important bulk texture is, okay, estimated, okay, bulk texture of the material is determined by using a Schultz reflection geometry concept. Okay, this is about X-ray diffraction. Okay, so when you talk about EBSD, okay, electron backscatter diffraction, it basically gives a surface information. Okay, only surface. Okay, the depth of penetration will be very small. The electron beam, this penetration will be very small. We are using secondary electrons. The penetration will be very low. So we can actually, okay, using this EBSD, electron backscatter diffraction, we have a special detector. Okay, it's called, simply called EBSD detector. Okay, it basically collects Kikuchi bands. It collects Kikuchi bands, like, okay, these bands will be collected, and, okay, on a particular location we may get this kind of band structure and establish, okay, wherever is seeing common, okay, intersection points. Okay, by taking those intersection points, we call it as a off transform, and band detection will be done and transform into some, give some half transformation by taking 5 to 6 points and compare, okay, match with the phase whatever is available in the standard pattern, and compare which is basically matching, okay, with this thing. So then accordingly we say index the thing. So after indexing, we can get a what kind of orientation with respect to specimen. Okay, we already defined rolling direction, normal direction, TD. Then we can establish this kind of orientation map. Okay, it's called colored inverse pole figure map. It's called, simply called orientation map. So each grain, okay, will be given. If the orientation changes, we'll give a different color. Okay, this is a legend basically indicates if it is a close to 111, we give a blue color. If it is 001, we'll give a red color. If it is 101, we give a green color. In between, we have a gradient in the color. Okay, each grain color indicates that this particular grain has this particular orientation. Okay, so if it is a red, we talk about it, this grain has a, okay, 00 orientation. If it is a blue, we have a 111. Okay, strong blue 111, somewhat we'll get somewhere. So it basically gives surface crystallographic texture of the material. Okay, so in the department, I think Professor Samazar has established, okay, facility. Both it has X-ray diffraction, bulk X-ray diffraction, bulk texture, and micro texture can be obtained. Okay, so both facilities, whatever I discussed, okay, Schultz reflection method and electron backscatter diffraction techniques are available. So you can, if we get an opportunity, you can visit that lab. You'll get a more idea about the electron backscatter diffraction. Okay, is it clear about the electron backscatter diffraction? Just I'm giving some important things. How do you collect? Okay, we decide. Okay, we send a beam on a specimen. It's at an angle. Put it at an angle, and you have a detector and collect these Kikuchi bands. Okay, these are actually scattering phenomenon. Okay, in inelastic scattering, I think might be knowing scattering phenomenon. So this elastic scattering and elastic scattering will be used to get this Kikuchi bands, and these Kikuchi bands are subjected to match with a standard information available in the software, and see whatever phase it's matching, then identify them, and we give the what kind of orientation with respect to your specimen orientation. Okay, this is how actually people established EBSD maps, orientation maps from the EBS. EBSD can be also used not only for texture, can also be used for actually identifying the type of boundaries. Okay, and what are you seeing any kind of low angle boundaries, high angle boundaries? Those can be seen. Okay, EBSD is now is gone beyond the limit. Okay, not only orientation, we can identify so much information by performing EBSD on a sample. Okay, here I'm talking about only orientation map. Orientation map, basically each grain can be will be known what type of orientation with respect to given sample coordinates. Okay, this is about electron backscattered diffraction. The next one, electron,
Sir?
even T, yes, please, yeah.
Sir, could you explain that colored structure again, where you were explaining the 111011, the blue, red, green color?
Yes.
Could you just go over that again?
Yeah, see, for example, if it is a blue here, this grain, it has, this is a kind of legend, it's a, if it is a orientation of this particular grain, with respect to your specimen orientation, we define specimen directions, so what is its orientation? Is it a 111? If it is a blue, because that means actually this grain is oriented, having a grain of 111 with respect to particular direction, rolling direction. With respect to rolling direction, we define a rolling direction here. Okay, so this grain has a 111 orientation. Okay, if we talk about red, if we take a red, anything close to that, we say this grain is a 001. Okay, so each grain has been identified what type of its what is its orientation with respect to rolling direction of the specimen. Okay, we are sending a beam in the normal direction. Okay, and we are seeing how these grains are actually oriented. Okay, with respect to we are defining. Okay, now your beam is actually coming in the ND direction, and we have a RDTD plane now. Okay, RDTD plane is there. So with respect, that's what we see. We do see this particular Kikuchi band. Okay, can we have different types of Kikuchi bands? We'll get look at here. Within this, we get different bands. Okay, so in this grain, what is a major thing? Okay, here we do see this particular band has a particular orientation. Okay, this Kikuchi bands will give you information about the what type of grain it is, what orientation of its grain. Okay, so this is how actually Kikuchi bands shape is going to change depending on grain orientation. Okay, so the majority will establish this kind of Kikuchi bands and compare and see that what type of grain it is. Then immediately once you know the orientation from the Kikuchi bands, we'll give that color to the particular grain. Okay, so EBSD can be used. Okay, you assume that is a single phase. If it is a single phase, the single phase, we know, for example, from the X-ray diffraction, theta 2 theta scan, we already know it's a nickel. Assume it's already know it's a nickel. That means we can directly give nickel phase and see. Once you know the nickel phase, you have standard patterns for nickel Kikuchi bands where it come 111 111 grain, what kind of pattern will come. If it is a 100 grain, what type of pattern will come for nickel? Already we know, so just match it, then we can give a particular color corresponding to that orientation. Okay, from theta 2 test scan, we do theta 2 test scan, we come to know this is a particular, it has a pure nickel or pure aluminum. Okay, you give to the software saying that this I'm trying to detect my Kikuchi bands correspond to nickel or aluminum. Okay, so for nickel, each orientation we already have a Kikuchi patterns, standard patterns. These are standard patterns for a given material, and match this particular each spot everywhere we get a diffraction. We take the electron backscatter diffraction each spot. and identify what type of pattern is coming. Okay, within the grain, we always get a same pattern within this grain. Once you move from this grain to other grain, we do get another, okay, electron backscatter pattern. We get another pattern, another different type pattern. Then that particular pattern basically corresponds to another grain. So we'll get another color grain. Okay. So what people do, EBSD, they do, okay, do kind of scanning. They do scan, okay, like this. So when it touches from here to here, we get a same type of pattern. Once you cross this grain, we get another type of pattern. That pattern change basically related to, okay, crystal, okay, orientation, crystal direction, basically, okay, crystal plane. Depending crystal plane, okay, we are going to see change in the, okay, Kikuchi band. So once you see change in the Kikuchi band, that can give you, okay, different texture. Okay, one has to have a standard, okay, information about that particular material. If you don't have standard thing, okay, one has to develop those things. It's a cumbersome process. It's not a straightforward. Okay, so most of the things already people have established database. Okay, for most of the metallic materials, data has been already present, available in the software. We simply just give, I'm trying to, okay, to get the EBSD pattern from so and so material. So then it will match those, okay, the corresponding crystal planes and directions, and give you the this kind of pattern. Okay, is it clear?
Yes, sir, understood. Just one doubt again, sir. Are these Kikuchi bands in any way related to the atomic number contrast that the PBSD provides, or
These
not?
are these are diffraction patterns. Okay, these are diffraction patterns. Okay, inelastic scattering. Okay, it comes from, okay, relatively thick samples. Okay, when you talk about thick samples, we get a inelastic scattering. That basically nothing but a diffraction. Okay, this diffraction spots. Okay, okay, particular plane will have a this kind of, okay, Kikuchi bands. If it is 100, it is a different. We get a different type of, okay, pattern. Okay, the number of, okay, band, we look at here, this is called Kikuchi band. Okay, this whole thing, okay, Kikuchi pattern, or simply called electron backscattered pattern. We do have complete, so many, each one of them give a Kikuchi band, and together, okay, all these things coming from a particular, okay, grain orientation. See, in a regular, we are seeing, okay, like this you are getting, okay, this particular brag angle we are getting, okay, like that, okay, for a particular orientation, for a particular pole, okay, we'll have, okay, this kind of number of bands will come. Okay, this is a diffraction, related to diffraction, scattering phenomenon, nothing else. The moment when you change another grain, another orientation, okay, the number of bands what is we are seeing are going to change, and their width is going to change. Without the band is also going to change because the scattering is different. If it is a different grain, okay, because all these things related to, okay, scattering phenomenon. Here I showed you particular, okay. If we talk about, okay, another, we may see another type of, okay, this is another, okay, kind of grain. So the band is going to change. Number of bands which are intersecting is going to change. Look at from here to here. The number of bands intersecting different, and the width of the bands are different here. Okay, this is basically coming from, okay, particular grain orientation. Okay, so they pick up what is the dominant one. Okay, that basically gives us, okay, a particular orientation of the grain. Okay, if you do, I think at TEM, I don't know, any of you are doing transmit electron microscopy course, there actually people talk about this Kikuchi pattern. Basically, there we talk about elastic and elastic scattering, and there we discuss, okay, how these bands are going to form. Okay, so if you about this electron diffraction, okay, is electron diffraction related things. That's why it's called electron backscatter diffraction, because we are using actually scattering, the backscattering phenomenon. In transmission electron microscopy, we use actually transmitted thing. Okay, there also we get, that's called actually, okay, selected area diffraction patterns. Here we are we are taking we are using a secondary electrons beams which are coming out, and diffraction, we are collecting only diffracted beam, okay, which are basically coming from a backscattered, okay, kind of thing. So when you send a electron beam, okay, the interaction is different, okay, with the material. So we do get different types of, okay, things, scatterings. What we are collecting only backscattered diffraction things we are collecting using a detector. Okay. Is it clear? So here basically what you are talking about, okay, we talked about theta to theta normal XRD scans and Schultz, okay, reflection method, which is quite is used commonly used for getting bulk texture of the material, and backscattered electron backscatter diffraction is used for obtaining, okay, surface orientation maps from the material. So even transmitted electron, okay, microscopy also used, transmitted electron microscope also used to get a information about the texture. Okay, we do get diffraction patterns. Here also we get a transmitted electron diffraction stand. Okay, we call selected area diffraction patterns. Selected area diffraction patterns. So typically, if it is a single crystal, we get, okay, this kind of spots on, okay, in the, okay, electron. If we collect a pattern, okay, we get a this kind of, okay, if it is single crystal, we get like this. If it is a polycrystal random, we get a ring pattern, we get a ring pattern. If there is some texture, if there is a some texture, we do see at some places we do see strong intensity, okay, we do see some strong intensity in a ring pattern, okay, but the ring is not fully, okay, bright. With some certain place we get a bright spot, certain place we get, okay, less intensity. So for example, this particular ring is a low intense as compared to this particular ring, okay. That means actually this ring, okay, this material is having a particular, okay, texture. Each ring is coming from a particular, okay, crystallographic plane, okay. Depending on material crystal structure, one can index these rings, okay, and see, okay, if you see there is a broken kind of thing and more intense thing, that means the material is a textured material, okay. So people also establish, okay, from the, okay, transmission electron microscope diffraction studies, okay, we have to collect diffraction patterns and see, okay, are we seeing a dot patterns, okay, or are we seeing, okay, ring pattern, or we are seeing any intensity change in the ring patterns, okay, that can give you, okay, whether material is a textured material or random material, single crystal. These are from the transmission electron microscope, can also get, but transmission microscope is like a localized information, okay. It cannot cover so many grains, okay. It cover only if it is a nanocrystalline material. If it is fine grain material, then it can cover so many grains. If it is a coarse grain material, we won't cover, okay. We'll always get individual grain, okay, information. It's a very limited information nowadays. Even, okay, we have a EBSD with TEM, okay. So within TEM, you can also get a EBSD patterns, but for very fine grain size materials, for very fine grain and small regions, we can get, okay, EBSD structures, okay, EBS orientation maps by using a transmission electron microscope. Okay. So I think these are kind of things, okay, we use to characterize crystallographic texture of a material. Okay. So the other important aspect now, how do you describe and represent crystallographic texture of a material? Okay, the whole concept comes from stereographic projection. Okay, so one has to have a knowledge on standard stereographic projections. Okay, and we can actually establish the poles from the standard, okay, stereographic projections. I don't want to discuss, okay, standard stereographic projections. It is part of a structure of materials. Okay, in structure of materials also people teach this stereographic projections. Okay, in a crystals we do get different orientations, okay, different planes. One can actually project them, okay, onto a 2D plane, onto a 2D like a circle, okay. In a 2D, it's basically in 3D we get a stereography. Within that we can project them particular things, okay. So depending on, okay, what projections you are taking, okay. So stereograms for cubic materials can be, okay, simple cubic material 001, 110, okay, 111. We have different types of stereograph projection, okay, stereography, okay. Stereograms, it's called stereograms, and we project them. Particular plane we'll project them, okay. So 100 plane we are projecting, okay. What kind of things will be there? Okay, these are the poles, the corresponding poles. 100, okay. These are, okay, orientations of the things. So one can project it, okay, just by putting a filter, and we can project it. We can project that particular, okay, circle, and we can get a, okay, a particular projections. So people usually see for simple cubic materials, we can project like 100 project or projection, 110 stereo projection, or 111. Okay, these are simplest, okay, we use to understand texture of a material. Okay, So I think if you need more information about it, one has to go through a textbook, okay, Kelly and Groves. It is on the structure of materials, okay. Very nice information, more details available on stereograph projection. Here, as far as this course is concerned, what we are talking about, the texture information usually derived from by projecting, okay, stereographs, okay. Standard stereographs will be projected 100 planes with respect to 110 planes or 111 planes. So one example here I'm telling, okay, just okay. So the description, okay, starts with, okay, pole figures, okay. By means of pole figure, okay, by using a pole figure, we can describe, okay, about the texture of a material. Okay. For example, if you see, if it is a random material, if it is a random material, if I have take a particular projection, if I take a particular projection, if it is a random material, we do see, okay, after diffraction, after, okay, X-ray diffraction, if you do X-ray diffraction, if you do bulk text X-ray diffraction, I get, okay, spots everywhere. That means it basically indicates the material is a random textured material. If there is a strong texture, if there is a strong texture, we do see certain poles, okay, will be high intense. Certain poles will be high intense regions. Okay, high intense regions can be seen in a particular projection. Okay, here what you are talking about, you have taken a specimen coordinates, rolling direction, transverse, okay, direction. Okay, and normal direction is a, okay, normal to this, okay, your laptop, if you see normal to this, okay, normal direction. So if you make a, okay, pole figure, this is called pole figure information, okay, we can see wherever we do see intense poles, that basically indicates what type of texture the material is having. Okay, so in particular, for example, we already know this is a cube texture. Okay, we are seeing, okay, a particular intense poles. If you take a one particular projection, if you see here, okay, if you talk about, okay, where I'm saying, if you take a 111, okay, see, particularly if you take any of these things, if you take a particular projection, okay, if there is a high intense poles, we are seeing, okay, high intense poles are developing, it basically indicates there is a strong texture is building up in the material. So one best, very good example about the texture change, okay, stacking fault energy. Stacking fault energy. Here we are talking about copper and brass. By adding zinc to the copper, we all of us know stacking fault energy is going to increase or decrease. Increase or decrease.
Decrease.
Decrease, sir.
Decrease. Okay. Look at here. Assume that, okay, all these materials were deformed. So same amount of strain by rolling. Okay, 90% deformation was given. Okay, for all these materials. Same amount of deformation, at room temperature, everything same. Only thing actually alloy content has been changed. Look at here, the texture. If you take a 111 pole figure, okay, I'm talking about a 111 pole figure. If I get, okay, from X-ray diffraction, if I get the intensive poles, okay, look at the pattern change. It's gradually changing, okay, and it's completely different here. The brass has a different, okay, kind of appearance than the copper. Okay, accordingly, people say, okay, if you see this kind of, okay, standard present is called copper component. The copper, actually copper component is building up here. If you see this kind of orientation, okay, in the pole figure, we do see brass component is building up. Okay, so with decreasing stacking fault energy, your copper component is going to gradually disappear and gradually start disappearing, and more brass component is going to build up in the material. Okay, so what is copper and what is brass component? Okay, so typically, okay, during deformation materials, we do see copper type component, brass type of component, S type components, Taylor components, Gauss components. Okay, these have a particular indices. Okay, 112 planes, family of planes, 111 direction. This is called copper texture. If it is, okay, more, okay, information is there related to 110 and 112. Okay, this is called brass texture. Okay, what does it mean actually? See, if you take, okay, brass material, if you deform 90%, we get a more amount of, okay, brass component than the copper component. If you take a pure copper, if I deform it, I do get more copper component than the brass. In between, when it changes from copper to brass, we do see development of S type of components during deformation of a material. In certain materials, we do see formation of a Gauss component. Okay, I said we already iron silicon alloy will have a Gauss component, which basically 110001. Okay, basically indicates Gauss component. Okay, so like these components, okay, we do see the texture components. Now, that's what you are talking about, texture components. Each component has a particular, okay, orientation relationship. Okay, here we are talking about particular, okay, Euler space. If we talk of Euler angles, phi 1, phi, and phi 2. Okay, each of them have a particular, okay, angles, 90 degrees, 35 degrees, 40 degrees. At these angles, we do see copper component is going to be more. Okay, so if it is more intense there at these angles, we do see brass component is going to be present in the material. Okay, so this is how actually, okay, but one of the problems with the pole figures, the problem here, okay, multiple, okay, we are seeing this kind of pattern. Simply people call it a copper component, but it's not only pure copper component. We also have several components, several other components also present in this particular, okay, pattern what you are seeing. Though the dominant is a copper component, apart from copper component, we also see several other, okay, components. Okay, so that's one of the drawback of a pole figure. Pole figure uses, okay, specimen coordinates RDTD, and okay, the poles will be taken into consideration to identify what type of texture the material has. So major drawback, there are so many components are there, those are going to get overlap each other. Okay, so that's a problem to identify actual texture, okay, of the material. What is the, okay, volume fraction of a particular component? It's not easy to get identified. Okay, but semi-quantitatively, we can say what type of texture is building up, and we can say, okay, we can just say, we can pinpoint this particular texture is getting built up in the material. But quantification is not easy by using a simple pole figure, okay, way of representing the texture of a material. I'll stop it here. Okay, we'll discuss about inverse pole figures, representation, and we also discuss about orientation distribution functions, ODFs. Okay, next class I'll talk about, okay, other way of, okay, representing texture of a material. Are there any doubts here? I'll stop it here.
Sir, the stereographic projection. So somewhere I learned about wolf net and everything. So
Yeah.
I mean, I need to revise all those things. Means how
It's
these
not
poles
required
are.
for this course. Is not required, but better
Okay.
understanding about texture. If you want to have a better understanding visualization, okay, you need to understand stereo projections.
Okay, sir.
Okay, for if you want to work on, okay, somebody wants to work on crystal texture, okay, how the material is changing, texture is changing as a function of deformation, as a function of reconstruction, all of them. You should have this kind of stereoscope understanding.
Okay, sir.
Okay, but as far as this course is concerned, you don't have to learn. Okay, you don't. Okay, it's good if you learn, but actually, this course actually I don't touch more about the stereography. I'm telling, okay, the pole figure information comes from the stereographic projections.
Okay, sir.
So could you go to the last slide? Sir, here if we want to know whether it's a copper component or a brass component or anything, so you have to kind of project the material in that particular plane, right? So for example, in copper, you have to project the material onto 112 plane, and then if you see some intensity in the pole figure, then you will know that it has copper component, right?
Yes, yes, you are
Is it?
right. So basically, I said Schall's reflection. Okay, you collect, okay, information at around 111 pole. Okay, that means we know that okay, for nickel or okay copper, it comes around 40 degrees. The first one. Okay, so what you do, we collect all, okay, 111 grains, okay, by just rotating the, okay, giving some kind of oscillation to sample, rotate the sample to 40 degrees, and collect the information and give some kind of oscillation. We get all 111, okay, related things. While collecting information, we do get, okay, this kind of pattern. The pole figure will be like this. Okay, one particular pole figure has a so many, okay, now apart from, okay, copper component, we also see several other components also present. One single pole figure is not sufficient to quantify the texture components.
So like for example, in the 111 plane itself, you will see copper component, then you'll see some brass component also, like along with that. So that's
Yes,
the
yes.
problem you say.
Yeah, but intensity may vary. Okay, look at here. So for example, if we take a triangle one, okay, your triangle is here. Okay, one triangle is here. Okay, these 4 triangles are there. These are related to copper. Okay, so here we have, okay, this intense, some intensity is there, but apart from that we also have a other intense things. Okay, here. Okay, so there are other things also coming. Okay, also contributing to this intensity.
Okay. So the table just shows that for a 111 bar plane, copper is going to be dominant, but at the same time, you can also see some other components in that 111 bar plane. So,
Yes.
okay.
So we cannot quantify it. Okay, you can say that at least, okay, qualitative. You can say that this particular texture component is getting stronger. Okay, but apart from, see, look at, because if you see only this triangle thing. Okay, this triangle. Okay, if you just connect these triangles, it's giving this kind of shape. Okay, typically. Okay, the based on
Yes,
that people
yes.
say, okay, it's a copper component, but we have to be very cautious. Apart from, okay, here if we talk about, okay, the other components also contributing to this high intensity regions.
Okay.
Okay, here for example, even if you
And
take, okay, here if you take here, there's so many not only copper component. Okay, we also have a, okay, gas component, brass component. Okay, many things are contributing here.
yes, sir. Sir, and how does the projection take place? Like when you say that you have to project it on 110 plane, 111 plane. So, how does the
No,
projection
no,
take place?
this basically what you are talking about. Okay, from the XRD. Okay, we collect the information about a particular pole. Okay, we collect the information about particular pole. Okay, we just rotate the sample such a way that we collect, okay, this particular pole. So then give, okay, we'll collect every information related to 111 pole. In that, okay,
Okay,
we'll
okay,
lot of other
okay.
related to 111 pole, whatever comes. Okay, those we are collecting.
Okay.
So in the spherical projection, okay, we are basically talking about 111. Okay, this projection. Okay, if we take here, okay, this is a, okay, particular stereo projection. Okay, so what I'm taking actually here, I'm just only collecting, okay, 111, 111, this different family of 111 planes.
Mhm.
Okay, so with what we are collecting only, we are applying filter and we are taking, okay, 111, okay, projections. Okay, whatever,
Okay.
okay, 111 peak supposed to come here, come here. Apart from that, we also get other things. Okay, in pole figure. If it is a pure 111, okay, if you take a 111, okay, projection, your all 111 peaks should be here. Okay, only 4, okay, will be there.
Yeah.
If it is a strong texture, okay,
Right.
if there is a strong
So,
texture of only 111, we get all intense peaks here only. Okay, we don't get any other things.
oh, okay. Sir, if possible, could you share the solutions of the assignment before the test? I got a bit confused with one or two parts of a question, so if you could maybe upload the solutions before it would be helpful.
Yeah, sure. I think, yeah, tomorrow I'll upload it. Fine. Yeah.
Okay, thank you.
Any more doubts?
Excuse me, sir. So I have doubt regarding the assignment question. So there in the assignment, when he has used two different
Yes.
routes for growing the grains. So there he has used for deposition and one is for just thermomechanical process. So in deposition, his data, the K value
Yes.
was sigma.
Uh,
I think sigma naught value was very close to the literature.
yes.
That was around 20 megapascal. So
Hmm.
what do we conclude here? I mean, does this process is more
Hello.
accurate or hello?
Hello.
Am I audible, sir?
I'm not getting. Yes. Yes. Tell me. Yes.
Yes, so I was
Yes.
telling
Yes. Now
like
it's clear. Yeah.
yeah, the scholar who has got the data with the deposition technique and with thermomechanical process. So I when I
Hmm.
plot, I got the sigma naught value that is very close to 20 megapascal that is reported in literature by using deposition technique. So what can we conclude here? Does it means like it is more accurate or it is giving?
No, no. See, usually deposition techniques will give you some stresses. Okay, some stresses are going to build up. Okay, though it's a pure metal. Okay, your sigma naught is more. Okay, What does mean? Okay, it's not only okay you are having a pure crystal effect. Apart from pure crystal grain effect, we also have a other factors like a residual
Okay, sir.
stresses. Residual stresses can additional stresses. The deposition. It's like we are talking about depositions. A lot of stress are going to develop.
Okay, okay.
In annealing, we are removing all the stresses.
Okay, sir. And the thermomechanical process, we were getting very small sigma naught value that was not
Yeah,
close to the
that's why
given.
it's fully annealed. It's fully annealed. Okay, finally it's fully annealed.
Okay, 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 sir.
Okay, so we don't have any stresses are present in them. But we are talking direct as deposition condition. Okay, in as deposition we'll get some stresses.
Okay, sir. And the
That's that.
reported data by Kane or some author who reported 20 megapascal. So I was not actually getting which process he has taken to give that 20 megapascal data or 0.14 K value.
That's fully
So that
annealed
was
material. Recrystallized
oh,
material. Sir. Fully recrystallized material.
okay, sir.
So I'll stop recording. Okay, I think if there are any doubts, you can stay back.